Welcome back to The Explainer. Today, we are diving into a really famous coding problem. And on the surface, it seems pretty straightforward, but it actually hides an incredibly powerful way of thinking. And it all starts with, well, some very aggressive cows. So picture this. You've got a line of stalls, kind of like spots on a number line, and you have a certain number of cows you need to place in them. The only problem, these cows do not get along. They're aggressive. Your job is basically to play peacekeeper and place them as far apart from each other as you possibly can. This right here, this is the heart of the puzzle. You need to arrange the cows so that the smallest distance between any pair of them is as large as it can be. It's a bit of a weird-sounding goal, right? Maximize the minimum. It definitely feels a little tricky to wrap your head around at first. Okay, let's make this real. Imagine your stalls are at positions 1, 2, 4, 8, and 9, and you're told, okay, place 3 cows. Remember, these guys will fight if they get too close. Your job is to find that perfect arrangement that maximizes their separation, creating total cow tranquility. So how do we even start? Well, probably the way most of us would. Let's just try stuff out. Let's pick a distance, see if it's possible to place the cows, and go from there. This is our first instinct, but you're going to see pretty quickly why it's not the best one. Let's start with the absolute easiest check. Can we place our 3 cows so they're all at least 1 unit apart? Yeah, of course we can. We could stick them at stalls 1, 2, and 4. The gap between 1 and 2 is 1, which is our minimum. So, yep, a distance of 1 is totally possible. Check. Okay, but our goal is to maximize that minimum distance, so an answer of 1 is pretty weak. Let's be more ambitious. Can we get them all at least 3 units apart? Yes, we absolutely can. If we place the cows at stalls 1, 4, and 8, well, the distance from 1 to 4 is 3, and the distance from 4 to 8 is 4. The smallest gap here is 3. So yes, it's possible. And that's a much better answer. All right, 3 works. You know what's next. We gotta push our luck. Can we manage to keep them all at least 4 units apart from each other? And here's where we hit a brick wall. Look, if we put the first cow at stall 1, the next one has to be at least 4 units away. So we put it at stall 8. Great. But now, where does the third cow go? It would have to be at stall 12 or more, and we just don't have any stalls out there. We can only fit 2 cows, not the 3 we need. So 4 is a no-go. So this method of just checking every single distance, 1, then 2, then 3, then 4, I mean, it works. We did find our answer. 3 is the biggest distance that gave us a yes. But you can see the problem, right? Imagine the stalls were 1,000,000 units apart. Checking every single number would take forever. There has to be a faster way. That slow one-by-one process just feels so inefficient. And it is. But it also gives us a huge clue. It turns out there's a secret pattern hiding in our results, and that pattern changes everything about how we should solve this. You know, whenever a solution feels that clunky and slow, it's usually a sign that we're asking the wrong question. We've been trying to find the right placement for the cows. We're searching through physical spots. But what if the answer we're looking for isn't a placement at all? And here it is. This is the big mental shift. Instead of trying to figure out all the combinations of where to put the cows, let's flip the problem on its head. Let's stop searching for a placement and start searching for a distance. We're shifting our focus from the physical arrangement to the abstract number we're trying to optimize. Now look what happens when we think about it this way. A really important pattern just pops right out. Think about it. If a distance of 3 is possible, then of course any smaller distance like 2 or 1 is also going to be possible. And if a distance of 4 is impossible, then any larger distance like 5 or 6 is definitely going to be impossible too. We have this clean break, a whole bunch of yeses followed by a whole bunch of nos. So now we have this beautiful sorted list of potential answers, all the yeses, then all the nos. And whenever you see a structure like that, one very powerful algorithm should immediately come to mind. Binary search. It is the perfect tool for this job. So instead of starting at 1 and counting up, let's look at our entire range of possible answers. The smallest distance could be 1. The largest possible distance would be the difference between the first and last stall, which is 9 minus 1, so 8. Our answer has to be somewhere between 1 and 8. Now, binary search doesn't mess around with starting at the beginning. It jumps straight into the middle of our range. The midpoint between 1 and 8 is about 4. So the very first question we ask is a minimum distance of 4 possible?
And we already know the answer to that. It's no. But here is where the magic happens. Because we know 4 is impossible, we also instantly know that 5, 6, 7, and 8 are also impossible. We don't even have to waste our time checking them.
So with just one single check, we just eliminated the entire upper half of all possible answers. Boof! Gone. We now know for a fact that our answer has to be somewhere between 1 and 3. That is a massive shortcut. And we just do it again. Our new range is 1 to 3. We check the middle, which is 2. Is a distance of 2 possible? Yes, it is. So 2 could be our answer. But maybe something even better exists, so we throw away everything below 2. With every single check, we cut our search space in half, letting us zero in on that largest possible yes answer incredibly fast. Okay, so this is a really clever trick for placing angry cows. But what's the big takeaway? Why does this matter beyond this one puzzle? Because this technique, this way of thinking, is a fundamental problem-solving pattern that you can use all over the place.
This whole idea is called binary search on the answer. It applies to any problem where you're trying to find a maximum or a minimum value. Instead of trying to build some complex solution from the ground up, you ask a different question. Can I just binary search for the answer itself? Can I write a simple check that tells me if a potential answer is possible or not?
And this is the question you should be asking yourself the next time you're stuck on a tricky optimization problem. Things like allocating books to students to minimize workload or finding the minimum shipping capacity needed for a set of packages. So many of these are secretly search problems in disguise. And that is the powerful idea to take away from our herd of aggressive cows.